But here the brightest part of the object was clinging to the sunward side. This growing archive of images raised more questions than answers. Each new observation added another layer of complexity, hinting at a structure or behavior that standard comet models just couldn't explain. The global, collaborative nature of this effort ensured the evidence was solid. It wasn't the product of a single instrument or observer. Instead, it became a shared puzzle, pushing astronomers to reconsider what a comet, especially one from another star, could even look like. Meanwhile, NASA's Jet Propulsion Laboratory was keeping a running record of 3I Atlas's position, speed, and trajectory. Every new image and measurement was folded into this massive global dataset. But as the object moved farther from the sun, a stubborn pattern started to appear in the numbers. It was something that couldn't be dismissed as a camera trick or a miscalculation. The equations describing its path began to drift from what gravity alone predicted. With each update, a small but consistent correction was needed. 3-1 Atlas was moving outward just a little bit faster than gravity should allow, as if something was giving it a subtle push away from the sun. The JPL analysts tried to account for everything: light pressure, normal comet outgassing, even the pull of distant planets. Yet the residuals, the differences between what they predicted and what they saw, didn't vanish. Instead, they revealed a persistent outward acceleration, about 0.0002 times the force of solar gravity. Over a single night, this is almost imperceptible. What stood out wasn't just the push itself, but its behavior. Both the sun's gravity and this extra force weakened with distance in exactly the same way, with the square of the distance from the sun. This meant the ratio between the mysterious push and gravity stayed constant, whether 3I Atlas was near Mars or halfway to Jupiter. In standard comet physics, non-gravitational forces like outgassing fade quickly as a comet moves away from the sun. But here, the math held up. The data demanded an explanation that went beyond what images alone could show. For the JPL team, this wasn't just a curiosity. The persistence of this outward acceleration and its precise inverse square relationship forced them to consider models outside the usual playbook. The puzzle had shifted from what the object looked like to how it moved, and what unseen mechanism could be responsible. At a distance of 270 million kilometers from the sun, even a tiny force can add up. The numbers from NASA SJPL showed that 3I Atlas was being nudged outward by a force about 2/100,000ths as strong as the sun's own pull. Over cosmic scales, that sliver of acceleration becomes tangible. If you multiply 270 million kilometers by that tiny fraction, the offset is about 54,000 kilometers, a gap wide enough to swallow several Earths side by side. A physicist named Avi Loeb and his colleagues took this calculation even further. They asked, what would that look like from Earth? This couldn't be a coincidence born of fuzzy data or wishful thinking. The geometry was just too precise. This is where the swarm hypothesis comes in. It proposes that a cloud of tiny objects is lagging slightly behind the main body of 3I Atlas. Math behind this idea is simple, and the match with the visual evidence is striking. For scientists, this kind of agreement between theory and measurement carries a lot of weight. It means the swarm model isn't just a wild idea. It passes a basic test of geometry and scale. The numbers don't guarantee a swarm exists, but they leave very little room for chance. A physical mechanism is needed to explain why the teardrop feature lands right where the math says it should. The puzzle is no longer just about what 3i Atlas looks like, but about why its structure and its motion are so tightly linked. Imagine a trillion tiny fragments, each no larger than a grain of sand, orbiting alongside 3i Atlas. A casual observer would never see them. But together, their collective surface area would be enormous, dwarfing the main nucleus. If these particles add up to just 0.1% of the comet's mass, observations from multiple telescopes support this. The brightness profile of 3i Atlas is dominated by a broad, diffuse halo rather than a sharp star-like point. The coma stretches outward with no clear boundary, and the bulk of the glow is concentrated in that region offset toward the Sun, the exact region predicted by the swarm hypothesis. This matches the data perfectly. The overwhelming majority of reflected light appears to come from something larger and more diffuse than a solitary comet core. If these numbers hold up, the swarm model becomes not just plausible, but necessary to explain what astronomers are actually seeing. What do you think this object could be? Let me know in the comments below.